Give me a thumbs up if you have looked over what you need to know at work. Maybe you made a note of something you need to practice or compute for, or look up on your own time, whatever it could be. All right, some of you to collect the quizzes themselves. I don't want the paper copy back because that's where you showed your work, because that's where you want to go back over some things. And go ahead and pull that up and I'll figure out the group of four. And you can see on the board. And the reason I wanted to go and give you your feedback is because there's a cumulative acid-base collision theory, which we basically know collision theory. We're going to finish up today. And equilibrium is the last minor topic that we're speaking to this week and beginning of next week. And so it'll be a short test. Like it'll be less than a page of the phrase. Because I just don't have time to do an hour and a half long test again. Okay. But I want to give you an opportunity to get some of those questions answered. We good? Okay. So, those of you who I asked to grab a laptop, go ahead and go to my website whenever you can. I just asked for a couple because we only need a couple throughout the lab. We're going to do an investigation of reaction rates. So you're going to be modifying a variable, and every group will have a different variable they're modifying. And upon modifying that variable, you're going to then measure a difference in reaction rate. After you do that, you're going to graph the data. And so your data should be very specific to your experimental variable, your independent variable, your dependent variable. Remind each other what that is right now. All right, you should know what IV and DV is referencing in general and then experiments. After you attain your data, you're going to graph it. And when I say graph it, you're actually going to put this on a group Google Slides PowerPoint so I can see the data real time, and you can present it in front of the class for about a minute each, because you're not going to have a ton of data, so it shouldn't take you that long to describe it and the relationships that are present. And that information, what you're going to be graphing, is going to be found under my website. So those of you who have the computer, you have the computers. That's not my website, is it? So you'll go down to Honors Chem Homework, and then down, you should see second period lab data. Okay, so that's a Google presentation. I will assign your group a number, like 1, 2, 3, 4, whatever. And I put the instructions here for you on the second slide. And that second slide looks like this. Complete your lab, and the lab instructions are at the tables, along with the equipment and materials. List the IV, list the DV, graph the data, and it can be just a line. You don't have to plot the data, because it might take us longer than we want it to, because we need a generalization. And then write a concluding statement. And all that information will be on one slide with your group number. You guys got it? Okay, so you're going to be in your pods, your table pod groups. I need to pull a couple people for makeup work. So Chris, Mir, Hannah, Corbin, Manal, stay. Everybody go find a lab station. In your table pods, you might need piece of paper, you can tear them out, it's okay. Share paper time. Here. Bring that basket with you. Just so you know, I'm not gonna do this. Alright, now I need to assign you your group. Part in the bucket. You are group 2. I mean, sorry, you're the group that's on the you do need goggles, send somebody with your material can some goggles. Alright, you have goggles on, you are reading your instructions before you begin. Read your little set of instructions before you begin so you don't goof up and make mistakes. So your data table there. If you need hot water, that means you need a hot plate. If your group needs hot water, you need to get it back going because it's not pulling itself up. You gotta get it going. Raise your hand if you need a thermometer. Raise your hand if you need a thermometer. Again, if you need a hot plate, you need to go ahead and get it set up. Do not put the cold beaker on the hot plate. Go down underneath.
No, which one you want to work in? You, that's you. Need a motor and a pencil.
I took a lot of time. Follow yours very specifically. Do not modify. Follow yours very specifically.
You have a motor
I was just gonna say, I'm gonna keep saying circle instruction. If you're making a hot bath and a cold bath and a room bath, whatever, it just needs to be a variation temperature. It doesn't have to be super hot or super cold. So if you're gonna need ice, you can even use ice until we get ready for me, okay? Alright, I'm gonna scare you. Just get ready. It's Friday, scroll down. Alright, somebody needs to start on the slide. You might want to start crafting your graph or your IDDD. Somebody needs to start crafting the graph. Modify your slide. Do not mess with other people's slides.
They're both 22 to 8 Celsius.
And like I said, I didn't want the data table. I saw the data table. I only asked for what? 3 things? IV, DV, graph, conclusion. Like the 4 things. The data is for you.
Alright, let's probably listen to us. If you want to listen to the time to resolve is alright, let's do it. You ready to avoid this? Alright, somebody start a timer. Alright. Can you start a timer?
You guys are ready? Nobody wants to wait for the lights on. It's a little better than you scoop. I'll take people you're gonna go. Why didn't you take all of them? It's always one you do. I know you wouldn't. You just put these wrong ones. These are next class.
5, 4,
I didn't say
3,
you
2, 1, go! Go!
Some days it's on the ground. You guys have an interesting ground. All right, you have 8 minutes to complete your slide and your data collection. 8 minutes. One. All right, so everybody on your WebQuest, you have your WebQuest on your desk, right? On your WebQuest, I'll tell you what I want you to write, okay? So have that ready and available, and you guys are going to be over here so that everybody can see you, okay? All right, so all I want you to write down is like G1, so group 1. And then you can put their ID, whatever variable they were changing, like they were purposefully changing because they wanted to see the result, and then the effect of that. Okay, that's it. All right, so you guys have a minute. That's it.
Okay. We our independent variables temperature. So basically, we had 3 types of temperature. We had a ice cold bath, so that was our temperature. That was 5 degrees Celsius, and then we had a normal room temperature one, and then we had a warm bath, which was about like 50 degrees.
So this is our data, and at 3 minutes and 58 seconds, that was for the cool bath, and then this is for the room temperature, and this is at 48 seconds, and then this was for the hot bath, and that was at 12 seconds.
So we concluded, based on the data, the higher the temperature, the less time Alka-Seltzer took to dissolve completely. So temperature and rate of dissolving have an indirect relationship.
Okay, so are you saying the rate of dissolving, meaning as
So
temperature increase,
the time it took to
dissolving.
dissolve it decreased.
So you're actually saying, so the temperature and the time of dissolving
Yeah,
have an indirect relationship?
Yeah.
So you're saying that does it speed up or slow down the reaction at hot temperature?
Speed up.
Speeds up. So you're actually saying increase temperature, increase rate.
Right.
Oh,
But-
never mind.
But the time is shorter.
Yeah.
So just think about what you're saying on that. Very good. Next group. 2.
We did ultra, whatever. Yeah, those tablets in water and with different stirring. So our independent variable was the stirring, whether there was no stirring, whether it was gentle, whether it was quickly. Our dependent variable was how fast the tablet dissolved. And for ours, we had middle stirring or gentle, took middle time to dissolve. Fast stirring took, took the least amount of time to dissolve. Fast stirring took the middle, and no stirring took the longest. We think that this data could have been skewed a little bit because the tablet could have been broken when it was thrown in, or there could have been like a different amount of grams in the tablet as they were broken. And in conclusion, basically it should be the more you stir, the faster it dissolves. But in our data, we had the gentle stirring was the fastest, while high stirring was in the middle.
I like that you pointed out the error that occurred, so that's very good to include in your discussion as well. Did one person stir the whole time?
We had two people stirring opposite. Well, one person stirred one and one person stirred the other.
So could that have been a variable? Right, so like remember we have controls and experiments to help us maintain data comparison, we'll use compare data. So different people stirring it slightly differently, maybe the broken up pieces are not, right? So someone in here doing eventually talk about surface area, so that would be a something to feedback off of. So we should see increased agitation should do what to rate? Increased rate of reaction. We should see increased agitation, increased rate of reaction. Thanks, group 3.
So our independent variable was the consistency of the Alka-Seltzer, either crushed or just solid as it was when we took it out of the package.
So this is the graph that we made based on our data, and the red line is, I think, was our beaker 2, which was the powder when we crushed it up. It took longer to dissolve, so that's why the line is a little bit more horizontal. And then this is the whole tablet when we just put it in undissolved, which dissolved much more quickly.
And we found that the powder dissolved slower than the tablet because the powder was like less density than the water, so the surface tension, it wouldn't break through the water, so it never really got that chance to dissolve, while the tablet went all the way into the water and was submerged, so it dissolved quicker.
So if we had maybe modified our procedure by putting the powder and the tablet in the beakers first, and then pour the water on top, what do you anticipate we would see? Because you know that this contradicts what we should have seen. Right? Everybody should understand we should not see this, but this is just the nature of how powder doesn't go through the surface very well. That's strict surface tension water. So assuming we modify the procedure, what would we have seen instead?
Had we modified it and done what you said and poured the water in, we would have seen that the powder would have dissolved quicker because it's already broken down a little bit, so it would have obviously dissolved much faster than the.
So what does you say broken down? But what term am I trying to pull out of you here? When you powdered it, what did you do to the Alka-Seltzer tablet?
Change the solubility.
No, it's all the same compound, right? So the solubility is not based on the way the texture, it's based on the compound.
Okay.
Somebody else?
The surface area?
Right, so what we're trying to see is that how does surface area impact rate of reaction? So theoretically, how should surface area impact rate of reaction?
The more surface area you have, like increased reaction.
Yeah, so more surface area, increased rate of reaction, right? Meaning faster reaction. And what the big word we have to always use when we're talking about reactions, increased surface area does what for us? Gives us more room for collisions, right? More collisions or higher rate of reaction. Okay, good job. Your next report.
So in our experiment, we had two different beakers, and one was filled with 10 milliliters of water, and another was filled with 150. And we placed Alka-Seltzer tablets in each of them. and our independent variable was the volume of water, and our dependent was the time to dissolve.
So an increase in volume of water led to a faster rate of dissolving. The more molecules of water were available to collide with the particles of the Alka-Seltzer tablet, and that allowed for more collisions and a quicker dissolving time.
Very good, very concise. So, what, I know you, it says volume of water, but generalize that, what variable are we actually modifying? Not surface area, that would be like powdering and something into small crystals or having a big crystal, that's the last crystal.
Like a solution.
And let's not say solutions, how about, there's one we spoke of yesterday. It's almost like you're just putting more reactant in there, right? So, this, it doesn't even have to be volume, it could have been more powder or more particles of something and whatnot, but you're definitely adding more particles of water to get more volume, or higher volume of water. So basically, increased particles does what to collision? Increases collision, and then that, therefore we saw increased rate of reaction. Good job, guys. Through what's next? 7. Let's go for 7. People.
Okay, so for the graph, we had 2 glow sticks, right? And we had 1 water of room temperature. Room temperature, and 1 beaker of water that was an ice bath. So basically, we stuck in the 2 glow sticks after we cracked them, and we found out that the colder the temperature, the dimmer the light is for the glow stick. And as the temperature went to room temperature, the brightness of the glow stick got, brighter.
So why was that? Why is the brightness changing? What does this have to do with reaction?
Because I'm gonna let one of my teammates take that question.
I'll wait on you. Someone jump in there. Okay, so temperature, start with temperature, right? Temperature is your variable.
Yeah.
Yeah, but what temperature now have what did you feel there?
There's a difference in kinetic energy.
Okay, and what does that do to the reaction?
It occurs faster
Why?
because as particles are moving faster, there's a higher chance that they'll collide.
Okay, so then this is very important. So can you guys put two bullet points on this part of your wherever you're writing? So 1, increased kinetic energy causes a what?
Increase in collision.
Okay, increase in frequency of collision. Okay. So can you guys demonstrate for me what high kinetic energy looks like and low kinetic energy looks like? Just use your hands. Okay, so is that high or low? I can't tell.
Oh, this is high,
Okay.
because it hits fast, and then this is low, because it hits slow.
That doesn't make very good. Okay, so hitting. Okay, read this with me. Hitting fast. Right. Don't even clap. Just graze. Okay. What's the difference in our first and second hand motions? How was that energy of collision? All right, guys. How was the energy of collision on the second on this one? Am I meeting activation energy when I'm hitting just grazing on each other? Okay, so temperature does 2 things. This is part, G of your request. It increases the frequency of collision, and it increases the energy of collision, which makes it likely to meet EA activation. Okay, how did that change our brightness?
Because the lower the kinetic energy was, the lower the brightness was.
Good, because the reaction just was not occurring at a rapid rate. Well, then, there's a reaction happening in space, believe it or not, and that's what's causing this flow of the next group, Rebecca. Please use some of that vocabulary so I'm on here again. Whoa! Please draw it on the board. Let's go. Hurry, let's go.
I'll do it now, be mad.
Let's go, guys.
This part right here?
Somebody, no. Somebody draw a graph on the whiteboard. No. Right, whiteboard. And somebody else starts saying, let's go.
Okay, so the independent variable is temperature of water, and its effect was on the glow stick. So as temperature increased, the duration of the glow stick's light decreased because it instantly faded out much faster at the total temperature.
What's your temperature did you guys have?
We had like, I believe 12 degrees there, 12 degrees Celsius and about 39 degrees Celsius for the heater.
It was warm at room temperature.
Okay. So tell me what the warm one again.
It lasts much longer, and it's like the light continued on much longer, while it almost immediately went out 3 minutes later for the colder one.
Okay. So you guys measured duration of light, not brightness. Okay. In the end, like say 20 minutes later, if you look at those glow sticks, who do you think would still be glowing? Actually, the one with the warm water would run out faster, only because it's reacting really quickly, and there's only so many chemicals in that little B2, right? So you're speeding it up, and it's going to wipe itself out very soon, whereas the slower one's going to slowly react. Maybe it'll react for an hour or two, and it'll actually make a slight brightness. Maybe you can't see very well. Oh, you guys sound like you actually don't get it. All right, thank you, group. All right, everybody grab a laptop if you don't have a laptop. Everybody grab a laptop if you don't have one yet. And I'm going to modify this a little bit, the instructions. I want you to see a couple of things. Go to my homework website, guys. And go to the rates graphical simulation. Okay, I want you to take a couple minutes and explore the features there first. Then I'll try to get everybody on the same page because we're just getting long. So it's just a simulator. There's only one thing you can click on right now. And I want you to run the reaction. Okay, play with it for a couple minutes first. Computer's booting up. Maybe you can look over to his shoulder for a moment. So you guys go for it. Select variables, change variables, modify some stuff, and make some observations first. It's the third link. Give me a thumbs up with the hand you're not using when you're on this little simulator. Alright, so everyone's going to pick two variables, and from those two variables, you are going to write down the variable you're testing and draw the corresponding graphs, two graphs, because you'll actually modify it from the control state, which is like the first part that pops up. You don't modify anything yet, and then the second time you test that variable, you're either going to increase or you'll decrease that particular variable. Do not do the variable that you tested in the lab. Okay, so think about the one you tested in the lab. Choose two other ones. Go. This shouldn't take you more than 10 minutes or less.
Can we just do it on the same paper?
You can do it on the same paper you've been working on. Yep. Whatever paper you've been working on. I just want you to see these graphs. If you did not do the lab, then you're still doing this with us, but you obviously don't have a limitation. You do this on your website if that's where you've been writing right now. That's totally fine. Keeping everything together. So don't modify it to a variable you've already utilized in the lab. Down. We're going to add a couple more thoughts and clarify some thoughts, and then we'll be done with the collision theory. We do have another lab tomorrow. Tomorrow's lab is more intense. Horseshoes. Okay, closer to shoes. All right, so give me a thumbs up. You understand there are three. Let's go ahead and make sure everyone's computers are shut for me, okay? Thank you. Shut your computer. Okay, what you should understand is that for a reaction to occur, things have to collide. And they have to collide with a certain condition, right? So those two conditions are proper orientation and sufficient energy, which we understand sufficient energy is just referencing the what? The activation energy. Show me an ineffective collision with your hands. Okay, so maybe something like just kind of glides past each other and they don't collide, break bonds, so we want them to collide with the correct orientation. So whatever has to collide together, atoms-wise, they can. They will make the new product, and that proof new product has the correct bonding structure. I think we already got that. We're pretty good with these graphs, right, guys? Understanding what goes on the graph? Okay. Oh, exothermic and endothermic. Which of these has more heat in the products? More heat in the products. Okay, so that means that there's a higher level of energy, or potential energy, I should say heat, but we call it energy in that whole. So which of these has the reactants has more energy than the products? Exothermic, okay, which has the products have more energy than the reactants. Products have more energy than the reactants. Endothermic, okay. I think we're good there, and you guys know how to calculate the heat differences. Okay, you're going to turn and talk in just a moment. I'm going to call on a different table for each of these, so get ready. So you're going to describe why the following occurs. So use some good vocabulary, try to piece it together one sentence, not like 5 sentences, okay? Lowering the concentration of the reactants will decrease the reaction rate. Everybody go, talk. All right, come back to me. 3, 2, 1. Corbin's table, go.
When there's more of the stuff, when there's more concentration, there's more stuff colliding, but when there's less concentration, there's less stuff colliding.
So less concentration equals less collisions, which does what to the reaction rate? Slows down. Okay, good. Gases react more quickly than solids. Talk.
I was going to say
All right, come back to me. 3, 2, 1. This is hopefully giving you a chance to practice before I call on you. That's the goal here, okay? Chandler's table.
Gases have high kinetic energy and move
Okay, there's two things that you're saying, right? So gases have higher kinetic energy, so move, that says move faster, and that causes what?
to collide together with each other.
Okay, so increased number of collisions. And, what's your group earlier, come on. That's going to get us there, but remember I mentioned specifically, we mentioned temperature first, that was your group. Temperature was related to kinetic energy, and then I said there are two things you always have to talk about when you talk about temperature, or kinetic energy. Frequency collision and energy collision. Okay, so gases have increased kinetic energy, moving faster, increased number of collisions, and increased energy of collision, which hopefully means they meet what, guys? Activation energy. Hopefully we meet that, therefore we would have an effective collision. All right, decreasing the temperature will cause a decrease in reaction rate. Go.
There will be a lower chance of colliding.
All right, this is kind of a repeat, but we can do this. Back to me, 3, 2, 1, Aiden's table. frequency of collision, and what? Awesome. All right, so just remember, if you're talking about kinetic energy or temperature, you have to mention both frequency and energy of collision in your explanations. Or if there's a multiple choice question, read it closely so you're making sure you capture all of that in your answer. 3 ways to that you can generally increase reaction. Wesley's table. Give me 4. Let's go. Ways to increase a reaction. Increase temperature. Somebody else? Say again. Add a catalyst. Okay. What else? What about it? Increase concentration. What else? Lower the. I'm gonna say the volume of the vessel. So like the beaker being a large beaker or a small beaker. Okay. Very good. What does a catalyst do to speed up the reaction? Anushka's table. Okay, and if you lower the activation energy, it's just more achievable. You can get there faster. We good so far? Okay, I feel like I've said this, I don't know, 15 times today. But collision theory is a very easy concept, but you have to know how to explain it. I think there's only 2 more things I need to tell you. Oh, okay. So tomorrow we're doing a lab that relates to literally measuring the rate of reaction. So think about the rate you traveled to school today. Talk in your groups. What rate did you travel to school? Depending on what time you left the house. Yeah. Okay, come back to me. 3, 2, 1. So Wesley, what was it? Okay, so theoretically, his speedometer is way off. Okay, 75 miles per hour, right? So anytime we talk about rate, it's always framed in the same way. It's change in apparently distance, right? So we can talk about traveling to school or traveling someplace. Change in distance over change in time, okay? And that's one that we see all the time. Change in distance over change in time. Do we travel distances in chemical reactions? No, like they're teeny tiny chemicals. They're not moving miles. They're definitely not even moving centimeters, maybe nanometers. But we don't even have measurement devices like that. So what we look for is quantity. We look for like concentration. So this is something that's new. Write this down someplace, okay? We need to understand that in chemistry, to measure rates, we usually describe them as a change in quantity or concentration. What's a good unit for concentration? Our favorite unit for concentration? Molarity, right? So put capital in there for molarity. So generally we're measuring the change in concentration over change in time. It's always for change in time though. What if our reactions happen relatively fast? What would be a good time unit for us? Seconds, right? Time can be in seconds. It could be in minutes. A lot of times we're not hanging around for an hour to watch a reaction occur just in our time frame, so we wouldn't generally use that. But it could be days and whatnot. So we're looking for either the change in quantity of the reactants. If the reactants have a color to them, let's say they're bright red, and over the course of a couple seconds, they go clear, you can see the color change from red to clear, so you can see that they're disappearing. But let's say the products were the ones that had the color. They went clear to blue. Well, blue is the product's color, so we would look for color changes. So sometimes we look for formation of products, while other times we look for the change of the reactants. So it kind of depends on what the experiment is. Okay, so now you're going to draw this graph. Draw it first, and I want you to talk it out. See if you can determine what it's supposed to be representing. It's a sketch, it doesn't have to be beautiful. Label what the top graph line and the bottom line represent. Now I want you to describe what it's trying to represent here together. Gosh, you guys are just chatting it up. See if you can interpret what that graph means. We're following somebody, so let's get an answer. All right, come back to me. 3, 2, 1. Kindle's table. I haven't heard from you guys. So we obviously can see concentration and time, right? So everybody, hush, hush. Everybody can see concentration versus time. So this graph is supposed to be indicating to us what? If we're looking at concentration versus time. Everybody. Rate of the reaction, right? And it's very obvious that we have both of the quantities of a reaction present. We have what and what? Products and, okay, so it's actually portraying both of them, so it's kind of nice we can see the whole picture. So what do you guys think this means, average table? Okay, so you're looking at a general picture, law of conservation of mass. So the products are being formed from the reactants, matter is being rearranged. I like that. No one's actually ever said that, so I like that extra detail. What else? What did you guys say, Bryce? Yeah, Bryce. Okay, so that kind of piggybacks off conservation, and that's the actual observation of what's occurring. Non-unstable. What else do you guys notice? Is it a straight line? What's going on with the line shapes here? Listen up. What's going on with the line shapes? What do you observe? Why is it curved?
It's a higher concentration.
Okay, so that's just going up though. So guys, you guys are math cookies, like smart cookies with math. You know this, not math cookies. Okay, so you're going from here to here. How does this slope compare? I don't know, I could draw a tangent line and show the slope, but you can still see it. So there's the slope of the initial reaction versus this down here. What's happening to the slope over time? Come on. It's what? It's flattening out, so you're saying it's decreasing. All right, so this is, I'm going to make this a little easier on us. Let's call these our 2 points here. What is the slope here? So how do you calculate slope? Rise over run. So what's the rise component here? About 0.04. So I'm going 0.1 and 0.06. The difference there is 0.04. Concentration, meaning molarity. What's the time difference? Well, it might be a little less than that, but 40 seconds. Let's go 40 seconds. Makes the math easier anyway. Okay, so what's the rate? Somebody have a calculator if you can't do it in your head. So give me the quantity. Like, what's the number? What's 0.04 divided by 40? There's a brain and a calculator, so make a choice. 001 what? Molar per second. Okay, so this is the initial rate of decay or decreasing of the reactants, and obviously that's going to be the same for the products. So we're just looking at this in a 1-to-1 ratio. Okay, do the same thing down here. Do this in your group though, because I'm not your math wizard. You can do this. This is a really rough estimation, guys. All right, so what's the change down here? So it's whatever what? Okay, so this is not quite to 0, but I understand you're trying to round it really well. 0.01 molar over what? So 150 to 250 is 100 seconds. What's this? Molar per second. Okay, so now you can describe what's happened to the rate over the course of the reaction. Okay, it decreased, right? We didn't have to calculate it, though. You could see it from the what? The graph slope. You could see the slope was really steep, and then it starts to flatten out. So why in the world is the reaction slowing down over time?
Because as the reaction occurs, there's less reactants.
Yes, that's it. It slows down because, and hopefully you're writing or imitating something on your graph and you're not just thinking about it, okay? It slows, so the reaction rate slows down because, what did you say, Bailey? Jacob just said it out loud. Not Bailey. I'm sorry, I'm looking at Riley saying Bailey. Riley. Why? Reaction rate slows down because the reactant concentration decreases. Good. And everybody, lower concentration of reactants means what? Less collisions. Always going back to that word collisions. All right. So, vice versa, products are increasing just simply, or products are increasing at a slower rate because there's less reactants colliding. Okay. Moving on. Okay. All right. So this is the same idea. I'm not going to do that one yet. All right, and if you don't know one of these factoids that I'm telling you now, I would write it down. I feel like this is a little redundant because it is the same stuff, just said differently. So we know the word effective collision, right here. Effective collision means what two factors must occur? Orientation and enough energy after activation energy. Sometimes the rate of reaction can be controlled by the nature of the reactants. If you've got like a molecule like glucose, C6H6, C6H12O6, you're going to have, I don't know, let's say 30 bonds. Okay, how does that compare to like water? Water's got what? 2 bonds. Okay, so sometimes the complexity of the molecule can affect how fast it reacts because you're going to break a lot of bonds in glucose versus 2 bonds in water to cause some rearrangement. So that's the complexity issue. We know how kinetic energy interacts. We know how surface area interacts. We know the catalyst. Yeah, we're good. That was the only new one I really want to tell you about, okay? All right, so that is collision theory in a nutshell. Open back up your laptop. Go to the yellow, green, whatever, wherever you are in that. I'm giving you 20 minutes. Let's go. Like I said, I'm trying to build in a little time every day for that, but if what you don't get done in class is on you. I don't have any tissues. Wesley, take some tissue. Get some tissue when you get in the bathroom. Bring it back. Okay. I just ran out yesterday. But, I mean, we have paper towels in here. It's a little softer. You can